So, discovering line spectra is certainly a boon to chemists, and as we shall see, to astronomers in many, many different ways. But it was in fact far more than that. Line spectra are part of a collection of experimental results that come out towards the end of the 19th century and into the beginning of the 20th century that usher in a second revolution in physics, in our understanding of the universe, perhaps comparable to the revolution that was ushered in what seems like a long time ago when we noticed this weird retrograde motion of some of the planets that led us to Newton and mechanics and gravitation and all of that. And in fact, the topic for this week is modern physics, and strictly speaking, what we refer to as modern physics is usually all of the insights that resulted from this revolution. Now, this is not a physics class. We're not going to go into too much detail, but we need a lot of those insights to understand astrophysical phenomena. And so let's follow a little bit of how this a new thread of experimental evidence was unraveled to tell us something amazing about the universe. What is going on? Well, what line spectra are, I argue, are going to be useful for understanding is the structure of an atom. Now, understanding the structure of an atom is a hugely important endeavor for physicists because atoms, after all, what is the brilliant success of the atomic hypothesis? The atomic hypothesis simplifies physics. It simplifies particle physics from a discussion of all the different kinds of chemical materials in the universe. All of that is reduced to an understanding of about 100 different species of atoms. There are about 100, on the order of 100 different elements. Each of those is characterized by a particular kind of atom. All known materials from water to DNA to you and me are produced by the interaction of these 100 species of atoms. So if you understood how to describe the dynamics of atoms, you would have solved the physics of the universe. In that sense, understanding what an atom is the fundamental question of physics. Now, the difficulty with this is that atoms are tiny. We cannot investigate their internal structure, what they are made of and how they work, by looking at them. They're far too small for us to see. So we need to use indirect techniques to understand how atoms work and what they are made of, and the indirect techniques are going to be spectroscopy. Spectroscopy. In what sense is that telling us something about the nature of an atom? This is not a surprise at all to physicists in the late 19th century, because they're very well familiar with this phenomenon, and they are going to understand line spectra as an example of the phenomenon of resonance. Resonance is very familiar to us. It's as familiar as pushing a child on a swing. So I have here a small version of a swing, and if I move my arm, I can make this metal oscillate, but not much. But if I pick just the right frequency at which to move my hand, then it's very easy to make it oscillate at a big amplitude. In other words, I was trying to inject energy into the motion of the metal here, and I was unsuccessful unless I was injecting energy at just the right frequency. Aha! From our new point of view on white light and colored light, we understand what this means. When we shine white light at a collection of atoms, essentially that's an electromagnetic wave that is trying to jiggle whatever charged constituents the atoms there have at all possible frequencies. Each color corresponds to a frequency. And if the atoms absorb energy only at some particular frequencies, then those are the resonant frequencies, the frequencies that are the frequencies at which those atoms are capable of oscillating. This is our new point of view on resonance, and we can see that in many examples with which physicists are very familiar. One example is a bow, which attempts to transmit energy to a string at all possible frequencies. The bow does not have a particular frequency. The physical nature of the string, its length, its tension, its weight, etc., determine at what frequency the string will actually vibrate, and therefore at what pitch it will produce sound. A slightly more dramatic and less pleasant example of this is in this famous video of a bridge across the Tacoma Narrows, which again is absorbing from all the frequencies contained in the wind that is blowing upon it energy at a frequency that is determined by the mechanical structure of the bridge, and when it has absorbed enough energy, then dramatic and potentially tragic consequences can ensue. So physicists are familiar with the fact that the collection of frequencies at which an object is able to absorb energy tells you something about its internal spectrum. We know how to read that for a string. That's a simple system. A more complicated, famous mathematical puzzle is, can you hear the shape of a drum? Those are all formal things, but in principle, this is how we can learn about internal structure of an atom. And in the case of an atom interacting with light, it's not mechanical oscillations, sound, that is interacting with the atom, but electromagnetic waves. And so we know that whatever it is in the atom that is interacting with the light has got to be charged constituents of what is otherwise a neutral atom. There's our first hint. Inside the atom, there must be charged constituents in order for a neutral atom to be able to interact with light at all, and these must have some resonant motions, and the frequencies of these resonant motions are what we measure as the line spectrum. Can we use that to learn something about the nature of atoms? Well, let's collect what we know already about the nature of atoms, and at the end of the 19th century, what we know for sure is that the masses of atoms are all approximately integer numbers. Remember, each element had an atomic number Z and an atomic weight A. The atomic number Z somehow determined the chemistry and the place of the atom, the element in the periodic table, but there was an atomic weight, and the mass of an atom, of all atoms, is approximately an integer times the mass of a hydrogen atom. Atomic mass unit was the name that people used. And so the first guess is, of course, if you have a collection of 100 different kinds of atoms and they all have masses that are integer multiples of the mass of a simple hydrogen atom, maybe atoms are made of collections of hydrogen atoms. Problem with that is a hydrogen atom is neutral, and so this doesn't explain the interaction with radiation. In 1897, great progress is made when J.J. Thomson discovers that the carrier of electricity in wires and in conductors is a negative particle, later called the electron, and the electron can be isolated and its mass can be measured, and its mass is about 1,000th the mass of a hydrogen atom. It's discovered that, in fact, atoms contain electrons. So here are the charged constituents that we were looking for. The light, and therefore mobile, charge inside an atom is carried by its electrons. Now, this is our understanding of the internal structure of an atom. Of course, an atom is neutral, so if there are negative electrons in there, there are also some positive charge in there, distributed in some way, and we can try to build a mechanical model of an atom by trying to match the forces inside in such a way that the resonance spectrum will match what we measure when we measure line spectra. And Thomson indeed tries to construct pretty elaborate such models. In the meantime, the understanding that atoms have electrons, and this is what carries the charge, leads to an understanding of chemistry. It turns out that an atom of species Z, so with atomic number Z, has in fact Z electrons, and that chemical binding is an electromagnetic interaction where atoms bind by trading, sharing, or deforming the distribution of their electrons, changing their electromagnetic profile, and this is how they bind. We understand what ions are. We see species of atoms with either positive or negative charges. This corresponds to an atom which either has had some of its electrons knocked out or has some excess electrons and is therefore either left with a residual positive or negative charge. And in principle, the understanding of chemistry is now that this is the science of electronic rearrangement, and the motion of the electrons and perhaps the sort of positive matrix of the atom in which they are embedded is what will determine the resonance spectrum, and we can try to, just as one would measure the length and tension of a string by listening to the pitch of the sound it makes, try to build models of an atom. Into this is injected, about a decade later, the following amazing result by Ernest Rutherford. Ernest Rutherford actually finds the positive charge in an atom by an ingenious experiment, and the result is shocking. It turns out that almost all of the mass of an atom and all of the positive charge is in a nucleus, as he calls it, and the nucleus has a size which is 100,000 times smaller than the size of an atom. So an atom has a size which is on the order of 10 to the minus 10 meters. All of the positive charge and essentially all of the mass of an atom is localized in a radius 100,000 times smaller, so in this tiny, very dense core. And then, since this has positive charge Z, we know that a neutral atom is therefore contains Z light electrons, and the way Rutherford conjectures that an object of size 10 to the minus 10 meters includes a very dense, massive positive core and negative light electrons, and the electrons don't fall into the core is, oh, wait, we know the answer to this. This is the same way that the solar system contains a central star and planets, which, while attracted to the sun, do not fall into it. Well, they are falling in. They're just falling in free-fall orbits. In the same way, one can construct a Keplerian model of the atom, where the nucleus is orbited by light electrons. All of the positive charge in the mass is in the center. The electron motion is therefore the motion of charge inside an atom. In some sense, our understanding is that now, since chemistry has to do with the motion of an electron, the nature of an atom is determined by its nucleus. If you have a nucleus of charge Z, leave it sitting around for a while, it will attract Z electrons, because at that point it becomes a neutral object. And so the chemistry is determined by the nucleus, and because the nucleus is not affected in chemical reactions, elements are immutable. The number of atoms of each species that enters a chemical reaction is equal to the number that exits. But we now have a mechanical model, and we can understand there are indeed periodic motions inside an atom. Somehow, the frequencies of these periodic motions ought to be the frequencies of the light that atom can absorb and emit. We have perhaps the beginnings of an understanding of what line spectra can mean, and the beginnings of a huge puzzle to which we'll turn next.